Hello and very welcome. My name is Dr. Lucas du Plessis. I'm a senior lecturer at the University of Pretoria in the Department of Mechanical and Aeronautical Engineering, and we are busy with a postgraduate module, Dynamics, msd780, that's the acronym. We are also nearing the end of this module. Today is already the 10th lecture, and we are busy with the 6th discussion on application examples, which Professor Nick Ravesh, the author of the textbook we are using in this module, included in his textbook, and he also included it in his MATLAB algorithm of the dynamic analysis program of the body coordinate formulation methodology which he proposes. Now, the textbook is titled Planar Multibody Dynamics, and it's the second edition which we are using. So the subsection in the textbook that we are dealing with today is subsection 8.1.5. The title of this subsection is Rod Impacting Ground. And over here you can see the schematic representation, and it is indeed a very simple example, but it demonstrates an intricate use of continuous contact impact as described in section 11.2 and equation 1142. So, subsection 11.2, continuous analysis of contact or impact. So, in the continuous analysis method, it is assumed that when two bodies collide, although the contact period is very small, the change in the velocities is not discontinuous. In other words, the velocities vary continuously during the period of contact as the contacting bodies undergo local deformations. To represent the local deformations in a simplified manner, it is assumed that the colliding bodies penetrate into each other in the contact region as depicted in the examples of figure 11.9a. So let's just talk about these two schematics in a bit more detail. The amount of penetration, which is denoted as delta, represents the sum of the local deformations of the two contacting bodies. Okay, so both bodies deform, and delta is the sum of the deformation of the two contacting bodies. The penetration starts in a compression phase with delta equals 0. Okay, so that's when contact is initiated, and delta is then obviously 0, and the penetration reaches a maximum value of delta equals delta subscript m for maximum. During the restitution phase, this is now when the deformed bodies return to their undeformed state. During that restitution phase, the penetration returns from delta max back to delta 0. Following an impact, the two bodies may remain in contact or they may separate. The penetration results in a pair of resistive contact forces acting on the two bodies in opposite directions, as shown in the illustrations of figure 11.9b. So, a contact force model can be viewed as a logical point-to-point spring damper that is only active during the period of contact. That's why Prof. Nick Ravesh refers to this point-to-point spring damper as a logical. There are phases or time spans where the point-to-point spring damper is not active. Okay, so typically when the two bodies do not contact each other, do not make contact, the point-to-point spring damper will be inactive. But when there is contact and deformation specifically, this point-to-point spring damper should be active. Alright, so we'll look at an example of how this is implemented. As a matter of fact, we already have looked at two examples where this logical point-to-point spring damper has been applied. And in today's lecture, we will revisit those two examples that we've discussed in lecture 5. So the characteristics of the logical spring damper element must be adjusted based on the material properties of the contacting bodies. So in sections 11.2.1 and in 11.2.2, we consider several models for a body contacting a rigid surface, and that we'll focus on in today's lecture. This is subsection 11.2.1, and then 11.2.2 deals with two bodies contacting each other. In other words, not a body with a rigid surface, but two bodies contacting each other. So, subsection 11.2.1, a body contacting a rigid surface. The simplest contact model to consider is the mass spring system shown in figure 11.10. Now there are three schematics represented here in figure 11.10, and we'll talk about each of those three schematics. The single body with the mass M moves toward the rigid surface. This is the left-hand side schematic. Okay, it's not making contact with the surface. It is busy moving toward the rigid surface. Now, as the body contacts the surface, this is now the second schematic, it deforms or penetrates the surface by an amount delta. This is the third schematic. Okay, so second schematic is at the time instant when contact is made, and now there's either deformation or penetration that happens, and that deformation or penetration is indicated by delta. So assume the deformation is represented by a spring of stiffness K. The penetration force can then be determined. This is the penetration force indicated in the free body diagram on the right hand side of figure 11.10. Okay, and that force can be determined as, very simple, it is the spring stiffness multiplied by the deformation. If we assume that the deformation also contains damping, the penetration force can be computed as shown here in equation 1132. And now we have a stiffness deformation term, and we have a damping rate of deformation term. Okay. dC is the damping coefficient, where K is the spring stiffness. dC is now the damping coefficient. Okay, so in the model of equation 1131, the penetration force varies linearly during both compression and restitution phases, shown as a solid line in figure 11.11a. Okay, so let's just talk about this figure 11.11a in a bit more detail. First of all, we noted that for equation 1131, where we only have stiffness, no damping, only stiffness, the penetration force varies linearly. Okay, and that's indicated by this solid line. The force, which is indicated on the vertical axis, and the penetration on the horizontal axis. Okay, so the force starts from 0 at a penetration delta equals 0. It reaches a maximum value and then returns along the same straight line back to 0, where at this point the body separates from the contacting surface. When we add damping to the model, as in equation 1132, which we showed a minute ago, the paths of the compression and restitution phases separate, as shown in the dashed line in figure 11a. So this is now the dashed line, and this is as soon as we have damping. This curve, this dashed line curve, shows that as the body contacts the surface, there is a non-zero penetration force due to the velocity of the body at the start of the compression phase. Okay, and this is indicated here on the vertical axis. Okay, so let's talk about dc minus delta dot. Let's talk about this non-zero penetration force. We mentioned that force is caused by the velocity of the body at the start of the compression phase. Now this velocity causes a penetration force, okay, which we already mentioned and showed here in figure 11a, where this rate of change deformation denotes the initial penetration speed at contact. The figure shows that the path during the restitution phase, okay, which is this phase over here, in the presence of damping is different from that of the compression phase. Okay, and this phenomena is called hysteresis. We also observe that near the end of the restitution phase, the penetration force becomes 0. Okay, this is now this area over here. It's near the end of the restitution phase. And this is where delta equals delta S before the restitution phase is completed. Okay, there's still a dotted line. Now, this is the instant at which the body separates from the surface while it continues to undeform. In other words, while it continues to change shape to its original shape. Now at this point, this delta S point, okay, since the contact force is 0, the acceleration of the body is 0, and therefore the velocity of the body is at a maximum. This means that during the final portion of the restitution phase, the model yields a tensile force. This is now this portion over here, as shown in the figure in dotted line, and this should not be applied to the body. Okay, because there is no force, as we've already mentioned. The body is not in contact with the surface or other body at this stage. Okay, so that was a discussion of both models represented by equations 1131 and 1132. Right, so just to continue a little bit on that, in the models of equation 1131 and 1132, it is assumed that both the spring and damper have linear characteristics. We may also consider nonlinear characteristics for the spring as shown here in equation 1133. Now, our reaction force is the spring stiffness multiplied by the deformation to the power n, where n is greater than 1 is an exponent to be determined based on the material characteristics of the body. Now, with such a nonlinear model for the spring, equation 1132 becomes 1134 if we now add damping. In this nonlinear model, a reasonable value for the exponent is n equals 3 over 2 or 1,5 if you like, as it will be discussed in section 11.2.2, and we'll get back to this section in our next lecture. The contact force versus penetration for the model of equation 1133 is shown as shown in solid line in figure 11.11b. Now, let's just talk about this figure in a bit more detail. So, similar to the linear model, in the absence of damping, this model provides the same paths for both compression and restitution phases. When damping is included, however, as in equation 1134, the model exhibits hysteresis behavior as shown in the dashed line. Similar to the linear model, the penetration force becomes 0 at delta S, which is the instant at which the body leaves the contacting surface, and so this portion of the restitution phase should not be included in the model. Okay, so with that said, let's now look at example 11.5. Now, the contact of a wheel or tire with the ground can be represented as a simple spring damper model as in equation 1132. Now, as shown in figure 11.12a, when the tire is not in contact with the ground, the spring damper element should be inactive. But when the tire contacts the ground, as in 11.12b, the spring damper should apply a force on the wheel. Now, examples of such models can be found in chapter 8 for the double A-arm and McPherson suspension systems. And you will recall in lecture 5, we actually looked at these two examples, and in today's lecture we will revisit them. So the double A-arm suspension, it's discussed in subsection 8.1.1, and as I've already mentioned, we did look at it, be it superficially, in lecture 5. And today's lecture we'll look at it in a bit more detail, specifically how the contact and the logical spring damper reaction force is implemented. Okay, so just to recap, the double A-arm suspension is shown in both figures 8.1a and 15.6a, and you can see the schematic on the screen here. It is a planar representation where its detailed description and the corresponding data can be found in section 15.6. Now, I have subsection 15.6 included in the mind map. We did look at all those details in lecture 5, so I'm not going to repeat it here. Suffice to just quickly, briefly show you figures 8.1b and 15.6b, as well as table 15.5. This contains all the geometric dimensions, and table 15.5 shows all the parameters that we will need and use to model this double A-arm suspension. I specifically want to revisit the input M file in forces. I did briefly discuss it in lecture 5, But let's just go through it again and identify specifically the logical spring damper force to simulate this contact behavior. Okay, so first of all, force S1 is a P2P or point-to-point spring damper that represents this spring damper between body 0 and body 1. Okay, and it is exactly or similar, very similar to the spring damper that we've discussed in lecture 9 when we spoke about the conveyor belt with a block that rests on the belt and the spring attaching the block to ground. Okay, so you're welcome to have a look at lecture 9. The details of how we formulate a point-to-point spring damper is or are discussed in lecture 9. Okay, so S2 is really our focus today. This is a user force, okay, and the user force has also been introduced and discussed in detail in lecture 9, where we spoke about the conveyor belt with the block resting on the conveyor belt. Okay, so in here we also make use of a user force, and we pass the stiffness, undeformed length and damping coefficient to this user force. These parameters, these values follow from subsection 15.6, okay, which we've discussed in lecture 5, and it's also included in the mind map, so I'm not going to revisit that. Now let's look at the mfile user underscore force. The first thing that Prof. Nikravich does is he calculates the deformation, and he does so by saying the deformation is the y coordinate. Okay, that's where this 2 comes from, y position coordinate of body 2. Okay, position coordinate is identified by this parameter r, and that position coordinate has 2 components, an x component, which is the first component, and a y component, which is the second component. So this is the y coordinate of the center of gravity of body 2. So this point over here. And remember, our global x-axis is placed on the surface of the ground. Okay, so that's why it makes sense to take that y coordinate and then subtract the undeformed length of the wheel, and that gives us the deformation. So if now comes the logical part, or the logic part, to determine whether the wheel is in contact and has actually deformed or not. And that's very simple. We just check whether del, this deformation that we've just calculated, is less than 0. If that is the case, then we can calculate this y reaction force. Okay, and there will be a stiffness component associated with the stiffness that we've passed to user underscore force multiplied by delta, plus there will be a damping coefficient or damping term. So it's the damping coefficient that we've passed to user underscore force multiplied by the velocity of bodies 2. Okay, the y velocity, y component of the velocity. That's why there is a 2 here. The parameter r underscore d is contains the velocities of all the bodies in the multi-body system. So we are looking at the y component of body 2's velocity. All right. So with that done, we can then say the force of the spring force damper only has a y component, and in this case it is negative Fy that we've just calculated. So what Prof. Nikravesh does here is he swaps, he changes the sign of Fy that has been calculated. And to understand why he does that is del, the deformation, is calculated here and it will be a negative value. So the stiffness multiplied by the negative value, we need to change the sign around because the force is actually acting upwards in the positive y direction. The damping component is a bit more subtle. Okay, the the second body's y velocity is positive in going upwards. Okay, so if this body, in other words, is moving and there's a negative velocity, so it's moving downwards, then the RD2 will be negative. Okay, and the same, and if you have the damping coefficient multiplied by a negative velocity, you'll get a negative force. So we need to change the sign of the second component as well. Okay, and that's why he first calculates Fy as the stiffness component plus the damping component, and he then changes the sign of that force. Okay, and then very simple, he just appends this FSD, spring force damper, or force spring damper, to the externally applied forces of body 2. Okay, so with that discussion of the M file user force, user_force, we can return to the input M file in forces. The last force is obviously only weight, and that we've been dealing with. We've been including weight or gravity in all our examples. Okay, suffice to say that if you do not specify S3.gravity as 9,81, DIP will use 9,81 as its default. And similarly, if you don't specify the direction of gravity as 0, -1, -1 being in the negative y direction as presented here, once again DIP will use that as its default. So it's, strictly speaking, it is not necessary to specify these two parameters. But be that as it may, I'm not going to go through the other input M files. You're welcome to refer back to lecture 5 where we've discussed all those input M files. I just want to refer us to exercises, actually only exercise 8.1. The objective of exercise 8.1 and then 8.2 was to illustrate and emphasize the importance of correcting the initial conditions. You may be certain about the initial coordinates, x and y coordinates, as well as the orientation of each body in the mechanism, but it is difficult and time consuming and unnecessary to calculate the initial velocities, x, y, and phi components of the initial velocities of each body in the mechanism. All you need to do when you run DIP is, when it asks whether you want to correct the initial conditions, is just type in a y for yes. The program then calculates. It firstly verifies the initial coordinates or initial positions and orientations of each body in the mechanism, and it then calculates the corrected initial velocities. And that is the emphasis, as I've already said, of these two exercises. Okay, and maybe just to end off with, so figure 8.2 shows the y coordinate of the wheel. It starts off at 0,35 and then it impacts the ground, it deforms, it comes back, and then it settles around 0,32 meters. Okay, and that was then the double A arm suspension, just a revisit of section 8.1.1, specifically looking at how we implemented the logical spring damper reaction force. Now let's do the same with subsection 8.1.2, the McPherson suspension. The implementation of the logical spring damper reaction force is exactly the same as that of subsection 8.1.1. So we'll briefly look at that. There's another little detail that I just want to show in this subsection 8.1.2, which we didn't deal with in lecture 5. So let's jump in. Right, so this model that you see here in figures 8.4 and 15.7a is the frontal view of a McPherson suspension system, and many automobiles are equipped with this type of front suspension. So it's very relevant example. Now, just before I move on, so in figures 8.4 and 15.7a, you can also see, as was the case for the double A arm suspension, the wheel is initially not making contact with the ground. Okay, and that's the reason for the logical spring damper force that we will implement. Okay, so 15.7 deals with all the details of the suspension. I'm not going to go through it. I did go through it in lecture 5, so you're welcome to have a look if you are interested. I just want to briefly mention figure 15.7b, showing all the geometrical detail that we need in order to create the model in the dynamic analysis program, DAP, that Prof. Nikravesh compiled. I also want to, and I'll refer back to table 15.66 later in this lecture, but I just want to highlight the fact that bodies 1, 2, and 3, the difference in mass of each body. So body 1 being the most heavy body, the heaviest body, at 20 kilograms. Body 2 is 10% of that at 2 kilograms, and body 3 is a quarter of body 2, 0.5 kilograms. So just keep that in mind when we look at the exercises, okay? Because the objective of the exercises was to model this multi-body system using composite joints instead of some of the bodies. Instead of body 3, we used a composite revolute translational joint, and replacing body 2, we inserted a revolute joint. The reason for me pointing this out is in today's lecture, we didn't do it in lecture 5, but in today's lecture, we will compare the results obtained by the different models. Each model having a different number of bodies. Now obviously, if you don't include, for example, body 3, your multi-body system will not take into consideration the mass of 0.5 kilogram and 0.2 kilogram meter square moment of inertia. It will not take that into consideration. But the fact that 0.5 kilogram is so small compared to the mass of body 1, it has a very little effect. It has a minimal influence. the same is not true for body 2. If you represent body 2 as a revolute joint, now all of a sudden there's a body that weighed 2 kilograms. It's not part of, or the mass of that body, and the moment of inertia of that body is not taken into account. And that does have a slight effect, and I'll show that in today's lecture. It may not, it may be worth your while to sacrifice a little bit of accuracy for speed of computation, but be aware of the fact that you are indeed making that compromise. It may be important, and the influence may not be significant, and then it's a good strategy. But if it is important for you to have very good accuracy and very accurate time response, then it is a better practice to include all the bodies with their mass properties, being weight and moment of inertia, and then wait a little longer for the simulation to run. So with that said, let's quickly have a look at the first exercise for this multi-body system. It is titled McPherson MP for McPherson suspension _A. Now this is the complete model. So we have a model consisting of 3 moving bodies. So we're not replacing any of the bodies with a composite joint. Okay, if you remember. Now in lecture 5 I went through all the input files. I'm not going to redo that in today's lecture. I just quickly want to show you in forces, just to confirm the way in which this logical spring damper reaction force was implemented. Right, so okay, so let's start. So S1 in forces is once again a PTP or point-to-point force, exactly as for the AA arm suspension, as well as the block resting on a conveyor of lecture 9. Okay, so nothing new there. The formulation is exactly the same, and we have discussed it now numerous times, so I'm not going to refer to the details here. This is the logical spring damper reaction force. It's a user force. We pass, once again, as for the AA arm suspension, we pass stiffness .k, we pass the undeformed length, which is equal to the undeformed radius of the wheel, and we pass the damping coefficient .dc, right, to user force. And basically an exact replica of the AA arm suspension. The first line of code, Prof. Nikravesh calculates delta, or del, the abbreviation for delta, as the position, the y position of body 1, okay, y being the second component, position represented by the parameter r, and body is 1, this is body 1 that we are interested in, and he then subtracts the undeformed radius of the wheel, which we've passed this, which we've passed to user _ force. Okay, so he subtracts that, he then performs a logical check, is del smaller or less than 0, and if it is, he then calculates Fy, the reaction force on the wheel. He does so by taking the stiffness that we've passed user _ force, we multiply it by the deformation, or del, which is an abbreviation for delta, and we add the damping component using the damping coefficient which we've passed user 2 into user underscore force, and we multiply that with the velocity of body 2, the y component of the velocity of body 1. Sorry, so it's body 1, it is the velocity r underscore d, and it's the y component. That's why there's a 2 over here. Okay, and then as we've done for the double A arm suspension, we change the sign from a negative. This Fy will have a negative sign. Why is that the reason, or why is that the case? It is the case because delta is negative, so a negative delta multiplied by a stiffness will give a negative force. And as I explained a little bit earlier, when the velocity, or the velocity of the wheel as it penetrates, as it makes contact and deforms when it makes contact with the rigid surface, that velocity will be negative because it's downwards. The wheel will deform as it moves down, and as a result of that deformation multiplied by the damping coefficient, as a result of that, the velocity, the rate of that deformation, which is now negative because it's in the downward direction, multiplied by the damping coefficient, so that this component will also be a negative. So we will have two negative components that we add, so we need to change the sign to a positive, and that's why Prof. Nikravesh puts a minus Fy over here. Alright, and then the next line is again a repetition of what we've spoken about in the double A arm suspension. We simply append the spring damper reaction force to the already existing externally applied forces that act on body 1. That's what this line of code does. Now, the next line of code, this line of code adds moments to the already, or the externally applied moments that act on body 1. Now, we didn't do that in the double A arm suspension, and I just want to point out the reason why that is the case. Now, okay, if you look at where the wheel is indicated here on the right hand side, you can clearly see that the force will act in the middle of the wheel, and there's a moment arm between where the force acts and where the center of gravity is, and that was not the case for the double A arm suspension. Let me show you. For the double A arm suspension, the reaction force was in line with the center of gravity, so there was no moment component because the moment arm is 0. The distance between the center of gravity and the location of the externally of the spring damper reaction force, that distance is 0, and because of that there is no moment. Okay, now I've actually already now explained how that moment component is then calculated. Let's start with the end of this line of code. FSD is the externally applied spring damper force, reaction force. Now this term over here, let's look at the term in the brackets, points 3.sp. So points 3 is the coordinates of this point C. Here you can see in the schematic in square brackets the number 3. I can quickly also show you in points. So point 3 is the third point, 1, 2, 3, and that is C, point C on body 1. Okay, so that's the point we're referring to. And if we now say point3.sp, it will have a C component as well as an eta component, which we've defined in points. Okay, so that's another way of saying or explaining what this point3.sp is. It's the local coordinates of the vector emanating from the origin of body 1 to the point C. Okay, so now let's look at S rotated, that function, and the transpose of S rotated. So to understand that, and I did refer to it in a previous lecture, but it is also explained in Prof. Nikravesh's textbook, and specifically on pages 17 and 18. This is part of Prof. Nikravesh's chapter 2, and there's also actually a proof to show that taking the transpose of a rotated vector and multiplying that with another vector is equivalent to taking the cross product of the original vector and this second vector. And that's exactly what we want to do here. We want to take the cross product of this vector with the externally applied spring damper force in order to get the moment that the externally applied spring damper force will cause about the center of gravity of body 1. So that's the input file user force. As you can see, very similar to what we've done in the AA arm suspension. The only real difference is the fact that we've got now an externally applied or a moment as a result of the externally applied reaction force. And we need to take that into account for the McPherson suspension model. So I explained all the other input files in lecture 5. We also looked at exercise 8.3, and in a minute or so I will be showing the combined results for exercise 8.3, 8.4 and 8.5. So just in anticipation of that, the end result of exercise 8.3 was to plot the coordinate and velocity of body 1 versus time, or alternatively the y coordinate and y velocity of point C versus time. Okay, and this is what these two plots look like. The y coordinate of point C starting at just less than 0.32 and stabilizing at around 0.24 meters. And the y velocity, you can see it starts from rest. It has a negative velocity, so it's traveling downwards. It then impacts the ground, and this behavior, velocity wise, in the y direction of point C, this is the transition phase until the y velocity then stabilizes at 0. There's no movement in the y direction after stabilization. So, alright, so with that said, let's carry on. I quickly want to have a look at the second McPherson suspension model, this MPB, where we now replace body 3 of MP_A. We replaced that with a revolute translational joint, if you remember. Okay, so I'm referring back to lecture 5. What I didn't do in lecture 5 is explain the details of a revolute translational joint. In order to do that, we need to look at subsection 7.2.4. The revolute translational joint is sometimes also referred to as a pin in slot joint. Figure 7.6 schematically illustrates three cases: 7.6a, 7.6b, and 7.6c. So let's look at 7.6a. So here you can see the revolute joint at point Pj, and that's where body J can now rotate relative to body I. Okay, body J can also translate relative to body I with this translational joint between bodies K and I, body K being indicated in a dashed line. Now 7.6b is similar, it's only swapped around. The difference between these two figures, and we'll talk about that in a little bit, is that for 7.6a this distance L is greater than 0, and for figure 7.6b the distance L is less than 0. The multi-body mechanical system shown in figure 7.6a and 7.6b can be modeled as a revolute translational joint between bodies I and J by eliminating the middle body K. Since there are two relative degrees of freedom between bodies I and J in figure 7.6c, we only need one constraint equation. So the two relative degrees of freedom between bodies I and J is obviously the rotation and the translation. Okay, so translation in a specific direction. So the translation that is perpendicular to the degree of freedom translation needs to be eliminated. And the way that translation is eliminated is by means of a single constraint equation. Now, to construct the constraint, the center of the pin joint is denoted as point Pj and point Pi and unit vector Ui are defined along the translational axis on body I. So point Pj is where the rotation happens, and then point Pi, this point over here, as well as the unit vector, this unit vector Ui indicated here, the point and the unit vector are defined along the translational axis on body I. Now, the constraint equation is found by requiring that the projection of vector D onto the axis perpendicular to unit vector Ui keep a length equal to L. Okay, and now we're referring back to this L that's indicated here in figure 7.6a and b. So this is a bit theoretical, and what I want to do is show you the derivation plus the end result of the derivation, which is the Jacobian submatrices as well as the right hand side of the acceleration equations. The reason why we're heading there is so that we can then come back to the program DIP, or the algorithm, the MATLAB algorithm of Prof. Nikravesh, DIP, and we can then see in DIP, in the input file, which parameters do we need to specify there so that the generic DIP can populate the combined Jacobian matrix as well as the right hand side of the acceleration equations and execute the dynamic analysis of our multi-body system. Alright, so bear with me for a little bit. And let me repeat what I just said. So we are now talking about the constraint equation. From the constraint equation, we'll get to the Jacobian matrix. as well as the right hand side of the acceleration equations. Right, so the constraint equation that which Prof. Nikravesh is defining is found by requiring that the projection of vector D, okay, and you can see vector D in all three schematics, okay, figure 7.6a, 7.6b, as well as 7.6d. So the projection of vector D onto the axis perpendicular to the unit vector ui needs to keep the length equal to L. Okay, and that's illustrated nicely here in 7.6a and b. So, in other words, what we can say, the mathematical expression or the algebraic vector expression for this condition that we just spoke about is shown here in equation 731, where once again we have this rotated function. So ui rotated transpose multiplied by d minus L needs to be 0. Alright, so all that is to say that the cross product between ui and the vector d minus the distance L must be 0. That's all it's saying in this equation 731. So in this equation, the length L must be considered a directional scalar. That is, it may be positive or negative, and that's illustrated here in figure 7.6a and 7.6b. For example, if we examine the vectors in 7.6a, L must be considered a positive quantity, but if the projection of D onto ui rotated is in the opposite direction of ui rotated, as in figure 7.6b, then L must be considered a negative quantity. Okay, so Prof. Nikravesh is doing an excellent job of explaining the mathematics in a lot of detail. Alright, so let's carry on. If the pin joint is located directly on the axis of the sliding joint, as in figure 7.6c, then L equals 0, and therefore its directional magnitude is no longer an issue. If we obtain the velocity constraint from the time derivative of equation 731, this is shown here in equation 732. Okay, so now we have, we've got the mathematical time derivative of the algebraic vector equation 731 here on the left hand side of equation 732. And if you are wondering about how this was derived, you're welcome to refer to chapter 2 in Prof. Nikravesh's textbook. Okay, the important thing is the right hand side of equation 732, and specifically these terms over here, because these terms are the components of the Jacobian submatrices, or these are the two Jacobian submatrices. The one on the left is the Jacobian submatrix for a revolute translational joint between bodies I and J, and this is the Jacobian submatrix of body I, and the Jacobian submatrix of body J is shown is the second Jacobian submatrix. Alright, and that's the next line of thought. Here you can see the two Jacobian submatrices. Furthermore, the right hand side of the acceleration constraint is found to be shown here in equation 734. So looking at the input M files for MP_B, McPherson suspension _B, specifically in joints, this second joint is our revolute translational joint, and here you can see we specify P on body I, we specify point P on body J, the index of that point, and we specify the unit vector on body I. Let's just tie this up with our Jacobian submatrices. So the unit vector, here you can see unit vector on body I. We need unit vector I rotated transpose, so we have that specified here in the input file. And then we also have once again unit vector on body I, the transpose. Then we've got this SPI, and this is this line of code over here. The point P index in body I is 2, so that's specified. We have that. Now what about D? Now D is simply the vector originating at point P J, point P on body J in other words, and going to point P on body I. So if we have point P on body J, which we have, this line of code here specifies it, and we have point P on body I, we automatically have vector D. Alright, so that's done, and that's the Jacobian submatrix on body of body I of this revolute translational joint between bodies I and J. Let's look at the Jacobian submatrix of body J of the revolute translational joints between bodies I and J. And here once again, unit vector on body I, that's specified here, no problem. And SPJ, apart from the unit vector on body I, and we have that as well. So very simple. Okay, so let's now quickly look at the right hand side of the acceleration equations. So here once again, equation 734, we've got the unit vector on body I, the dot product of the unit vector of body I, and that dot product is calculated by DAP. As long as you specify the unit vector on body I, the dot product is calculated inside DAP. Let's look at the other terms. So we've got D again. Okay, and if we have, as I said before, if we have the coordinates of point PI and PJ, we've got D. Phi I dot is once again calculated by DAP, the velocity, the angular velocity of body I. And here we've got 2 times the time derivative of D rotated. Now once again, if you have D, this D rotated is calculated by DAP. So there's no problem there. UI, once again, is already specified here in our input file. And then SPI dot, SPJ dot, Phi I dot, and Phi J dot, all those terms are calculated by DAP. What's important for SPI and SPJ dot is that the SPI and SPJ without the dots need to be specified, and as I've said a number of times already, those are specified in our input files. So to wrap up, in terms of our Jacobian submatrices, as well as the right hand side of the acceleration equations, we've got everything that we need specified here in the input file in joints. So to wrap up this second model of the McPherson strut suspension for exercise 8.4, how the forces were specified, and this is exactly the same as for McPherson suspension underscore A. So what you see here is the input M file for in forces for McPherson underscore B. Okay, and it's exactly the same as before. So we've got a point-to-point externally applied force, and then we've got the user force that specifies the logical spring damper reaction force of the tire. And then lastly we've got weight. Okay, and this user force, we discussed that when we spoke about McPherson underscore A. It's exactly the same. That was McPherson suspension underscore B. Let's quickly look at McPherson suspension underscore C. Now what we have here, we only have a single moving body connected with a revolute translational joint that we've discussed in McPherson suspension underscore B, and then this body too is replaced by a revolute joint. So let's see how that is done. The externally applied reaction force, spring damper reaction force, is handled exactly the same in McPherson suspension C as it is done in McPherson suspension B, as it is done in McPherson suspension A. Exactly the same. The thing that I just want to clarify here, which I didn't do in lecture 5, is I just want to show you the details of this revolute joint. Okay. Now in order to do that, let's have a look at subsection 7.2.3. Consider the three bodies connected by two revolute joints as shown in figure 7.5a. This system requires 9 coordinates, 3 per body, and 4 constraint equations, 2 per revolute joint. Therefore, this system has 9 minus 4 equals 5 degrees of freedom. This system may be represented by the kinematically equivalent system shown in figure 7.5b, where body K in 7.5a and the two revolute joints are combined to form a revolute joint as a link. Okay, and that's shown here in figure 7.5b. Now, the configuration shown in 7.5b requires only 6 coordinates for bodies I and J, 3 per body, and a single constraint equation. Therefore, this equivalent system also has 5 degrees of freedom, and that's equated by taking 6 coordinates minus 1 constraint, giving you 5 degrees of freedom. Now, to formulate the constraint equation for a revolute joint, we take advantage of the length of the link being a known constant L. Okay, L is not the known constant L is not indicated here in figure 7.5b, but this vector D is indicated. And obviously the magnitude of vector D will be the length that we are referring to. So let's see how Prof. Nikravesh has done that. As shown in figure 7.5b, the centers of the two pin joints are denoted as points Pi and Pj. Vector D is then Rpi minus Rpj, connecting these two points, and this vector must keep a constant length. So it's now very simple to see that the constraint equation can be written as D transpose D minus L squared equals 0. Okay, and this is the dot product of D with itself. Okay, so if you take the dot product of a vector with itself, you get the magnitude squared. Okay, and that's where this constraint comes from. So we take the dot product of D with itself and we subtract the square of the magnitude L, and then it must be equal to 0. That's clear enough. This is a well-defined constraint with the following time derivative. Okay, so superscript R dash R standing for revolute joint. It has a single constraint equation. That's why there's a 1. phi dot equals d by dt of d transpose multiplied by d. Okay, now applying the product rule of differentiation as per equation 252, we obtain that, and this is equation 252, so the time derivative of A transpose B is A dot transpose multiplied by B plus A transpose multiplied by B dot. Now if we apply that to this constraint equation that we've just defined, or sorry, if we apply the product rule now to the time derivative of the constraint equation that we've just defined, this is shown in this block over here. So you can go through the maths to check it. I'm confident that it is correct. It just shows you that d by dt of d transpose d equals 2 d transpose d dot. And this is the point we're heading at. And we note that the coefficient 2 will continue to appear in front of every term in the Jacobian matrix and also on the right hand side of the acceleration term, and we don't want that. Okay, we don't want that. So how do we eliminate that coefficient 2? We simply redefine or modify the constraint equation that we defined over here as superscript r dash r for revolute joint, comma 1, a single constraint equation. Phi is a half or 1 over 2 multiplied by, in brackets, d transpose d minus L squared, and that equals 0. And this is equation 724. We can express these constraints in a slightly different form by defining a unit vector u as the vector d divided by the magnitude of the vector L, and use it to replace one of the d vectors in the constraint equations, which results in the following revised form of the constraints. So we're revising the constraints once more, and you will see where we're heading. Once again we are heading towards what does the Jacobian submatrices look like, and what do we need to define in DAP, the MATLAB algorithm, such that the Jacobian submatrices are defined and known in DAP and the right hand side of the acceleration constraint equations. Alright, so bear with us with all the maths. Alright, so this is the third revision of the constraint equations. The time derivative of this constraint, referring to equation 712, which I've shown here, is given by equation 728, and this is where we wanted to get to. Okay, this resulting Jacobian submatrices, U transpose SPI rotated, and minus U transpose SPJ rotated. Let's look at how Prof. Nikravesh defines what parameters are defined in the input file in joints for this McPherson_C suspension. Okay, and here you can see it's a revolute translational joint. Point P on body I, point P on body J, those 2 points are specified. Okay, and with those 2 points known, we have the vector SPI. Now, let me just show you quickly. If we have point PI, the vector SPI originates at the origin, or the C of G of body I, and ends at point PI. And similarly, the vector SPJ originates at the center of gravity of body J and ends at point P on body J. Alright, so we have vectors SPI, and we also have vector SPJ. So plus then obviously this unit vector on body I. So everything we need for the Jacobian submatrices are specified in the input file. Let's quickly look at the right hand side of the acceleration equations. Prof. Nikrawest gives those terms in equation 730. Okay, so let's quickly have a look. We have the time derivative of vector u on body I, and with vector u on body I defined, DAP calculates the time derivative. So there is not a problem there. Then we've got the vector d dot. Now vector d is with points P on body I and P on body J known. We've got the vector D because the vector D connects those 2 points with each other. So with the vector D known, DAP calculates the time derivative of that vector. Okay, U rotated transpose, that's known because we've specified unit vector on body I, no problem there. SPI dot, phi I dot, SPJ dot and phi j dot with points P on body I and P on body J known and defined. DAP calculates SPI dot and SPJ dot, and DAP also calculates the angular velocities of bodies I and J. So everything is defined for us to run this simulation. Okay, and for completeness sake, I just want to show you once again for McPherson _C, our input file in forces look exactly the same as before. We've got the point-to-point force, externally applied force S1. We once again have the user force. This user force is the logical spring damper force that is applied to the tire. So once again, user force looks exactly the same as before, nothing new there, and then obviously also weight is applied. So let's end off this lecture by comparing the results of the 3 exercises that we spoke about in lecture 5. Okay, so just referring you back to table 15.6. Now, body 3, this body over here, has a weight of 0.5 kilograms. In exercise 8.4, we've removed that body and replaced it with a revolute translational joint. So what we are expecting to see is that the results between exercise 8.3 and 8.4 should be very close, because 0.5 kilogram compared to 20 kilograms of body 1 and 2 kilograms of body 2 combined is not a lot, right? We're not expecting a major difference. However, for exercise 8.5, we are now also replacing this body 2 with a revolute joint, and body 2 has a weight of 2 kilograms, which is a bigger percentage, 10% roughly of the multi-body system. So we're expecting there a slightly bigger variance in the results. And the good news is that is exactly what we see. So I've done, if I can just go there quickly, I have combined the plots of the y coordinates of point C. Okay, and this is what you see. You can't see much on the full simulation. But in the zoomed section, and I've just looked at this top section here. Here you can clearly see the blue line is of the complete multi-body system, all 3 bodies all the mass properties, everything is there. The red dashed line is where we've replaced body 3, which weighs 0.5 kilograms, with a Revolut translational joint. And you can see a slight offset from the 3-body simulation represented by the blue line. The dotted line here, and I think it's a color yellow, it's not very visible here, but the dotted line is now where we've also replaced the bottom link, which weighs 2 kilograms, with a Revolut joint. And now you can see the impact of that is more significant. Okay, so, and the same goes for the velocities. Here the difference is even, well, you can see it on the full simulation, but also clearly here you can clearly see the effect in the zoomed section. So the blue and red dashed lines are close together. Okay, that's the difference between simulating the full system and removing the 0.5 kilogram body with a Revolut, replacing that 0.5 kilogram body with a Revolut translational joint. And then if you also replace the bottom link, which weighs 2 kilograms, with a Revolut joint, the influence is more significant, and that's shown here with this dotted line. Alright, so very interesting results. It reassures us that the simulations are accurate, and once again, congratulations to Prof. Nikravesh for his excellent lifetime of work in multi-body dynamics, and the wonderful algorithm and text that he's made available, and also the wonderful textbooks that he has written. And with that, thank you very much for watching, and I'll see you in the next lecture.